15 asks, what type of reaction is this? This is maybe the trickiest one, and I overheard some of you talking in the auditorium when we did this one. Why couldn't this be double replacement? Because it looks like two compounds. Why couldn't they switch partners? Well, if you think about it, it'd be calcium and sulfur switching partners. And in this case, they both have the same partner already. So they couldn't really exchange partners and both be dancing with oxygen all over again. That doesn't work. So it can't be double replacement. It can't be combustion because we don't have a fuel or oxygen, so that's out. And it isn't going to be decomposition because, again, decomposition tends to be when one thing is going to break down into two or more things. All that's left is synthesis. And in fact, if we think it through, we can come up with the products by name and by formula. The name of my product would be calcium sulfate, CaSO4, in the synthesis reaction. Number 16, we've got CH4 and oxygen combining to make what? Well, this is a combustion reaction. That's the simplest, lightest fuel we can think of, basically. Methane, about the simplest fuel gas that there is. And carbon and hydrogen and oxygen coming out the other side will give me, well, it really could be any of these choices, I suppose, if I didn't know anything else about combustion. But knowing that combustion always produces water as a gas, that leaves me A and D as my choices. And knowing that combustion always produces either carbon dioxide or carbon monoxide, the only good choice I've got here is letter D. Carbon dioxide and water being produced, so that's letter D. 17, what type of reaction is this? Well, this is one compound breaking down into potentially two or more things. If we're given one compound on the left side, there's really only one kind of reaction it can be, and that's decomposition. It doesn't ask you here what those products are, what kind of reaction it is simply, and that's letter B. Just for the record, you'd be making water and carbon dioxide when this comes apart, as was mentioned earlier on. 18, we're taking hydrochloric acid and putting it together with potassium hydroxide. Now, not only is this a double replacement reaction, hydrogen, chloride, potassium hydroxide, essentially, switching partners, it's a specific kind. It's that neutralization kind of double replacement reaction, where when the two partners switch in a neutralization reaction this way, we end up making water. Hydrogen goes with hydroxide, HOH, and that's water. So we're going to make water as our product. And right off the bat, I can find that only letter B gives me that. The only other product that I could make then would be if the potassium and the chloride got together. That gives me potassium chloride. So KCl and water, that's letter B in a double replacement reaction. 19. Which of the following is least likely to decompose and produce a gas? Well, all of these could decompose. The question is, which will not produce a gas, we expect? Well, look through here. I've got calcium, carbon, and oxygen. When that decomposes, if I think about it, it's going to make carbon dioxide, which is a gas. And HNO3, that's an acid. When acids decompose, they tend to make water and a non-metal oxide. Basically, almost all non-metal oxides at room temperature will be a gas because non-metals with non-metals tend to like to make gases. In this case, we'd get nitrogen and oxygen together at the end in dinitrogen pentoxide, which is a gas. Even if you didn't know that, though, let's look ahead to the next one. Potassium and chlorine, those are two elements that together make a salt, but when I pull them apart, I would get potassium and chlorine, a gas. Chlorine's a gas. And again, even if you didn't necessarily remember that, hopefully you'd look at letter D and say, here I've got iron and sulfur. And somehow iron and sulfur just can't be gases, typically, when these things come apart. Iron's a metal, sulfur's a non-metal that happens to be a solid at room temperature. Now, could it come out as gaseous sulfur? Probably not, because sulfur tends to combine with oxygen really fast, and you wouldn't get sulfur by itself. When we take iron sulfide apart, we're likely to get iron and sulfur maybe as liquid sulfur at the best. So we're not going to get a gas from letter D. Neither one of those is going to come out as a gas. Number 20, we've got magnesium nitrite decomposing. How does this work? Again, this is a ternary salt, so we're going to get a metal oxide and a non-metal oxide. Well, that leaves me B, C, and D as my choices. Those are the only three choices now that have a metal oxide, magnesium oxide, and a non-metal oxide with nitrogen and oxygen together. So A is out. What about B? Well, if I look at B, magnesium and oxygen going together wouldn't make MgO2 if we call it magnesium oxide. So magnesium oxide is MgO, not MgO2. So B is out. That leaves me with C and D. And this is where I have to think about what is nitrogen's charge in the original compound, and what will it be then, that same number at the end? Well, if I go through here and think about MgNO2, 2, I've got 1 magnesium. That's contributing a +2 to my oxidation number total. I've got 4 oxygens that are each contributing a -2 to my oxidation number total. 4 oxygens times -2 makes -8. The magnesium contributes +2. So I have -8 and +2 so far. That means overall, the magnesium and the oxygens put together give me a -6. The 2 nitrogens that are in this compound have to give me a +6 in order to balance this thing out. 2 nitrogens that give me a +6 total means each nitrogen is worth a +3. So magnesium's +2, nitrogen's +3, and oxygen, as always, is -2. Well, if nitrogen's +3, and I bring it across to the other side and put it together with oxygen at -2, a +3 and a -2 will combine in a 2-to-3 ratio, and that's what we see in choice letter C, MgO plus N2O3. Now, this is a complicated idea with oxidation numbers for some folks, and this is frankly what hangs people up on decomposition and synthesis reactions. If you're still struggling with these oxidation numbers, please come and see Mr. Mitchell or myself ASAP for some help in order to get this problem solved. It's not hard to get you figuring it out if you sit down with us for 10 minutes, and we'll have you straight on the way to success with these decomposition reactions. 21, the likely second product here will be most likely a precipitate, a gas, water, or a soluble salt. Well, what's the other product going to be? I've already taken the magnesium and the nitrate and put those together to make that product. What's the other product going to be? Well, it's going to be HBr, hydrogen with bromine. Hydrogen with bromine are those 2 nonmetals that are bonded through a covalent bond or maybe a polar covalent bond. When we have 2 nonmetals bonded together, well, that's not water. We don't have water here. And we don't have a salt. Remember, a salt will be a cation with an anion. Hydrogen bromide is really not a cation with an anion. It's 2 nonmetals that have found a way to bond together, covalently or polar covalently. And in this case, hydrogen bromide comes out as a gas. Hydrogen bromide gas when 2 nonmetals. So in question 22, you've got one substance that can only do one thing, and that's decompose as far as we're concerned. So what you need to do here is recognize that this is following one of our kind of example equations, which would be a metal, a nonmetal, and an oxygen together. So we think about that as metal, nonmetal, oxygen. Our formula XAO, where X is a metal and A is a nonmetal. We're going to get XO and AO, kind of our general equation. So if I look at my options, only a couple of these could even be possible. We have the metal potassium with oxygen and the nonmetal chlorine with oxygen. A and B are the only choices we've got. Already in C and in D, we don't have the right elements put together at all, so those are out. As far as figuring out which of these other 2 is correct, we need to go back to the compound itself and look at the charges on each element. Potassium's oxidation number is always +1. Oxygen is almost always -2. And if that's the case, chlorine in this case, in order to make KClO2 be a compound that comes up with no overall charge, chlorine would have to be a +3. So +1 and +3 makes +4. Together a total of +4. And the 2 oxygens make a total of -4. So chlorine here is a +3. If I bring that across to the other side, my potassium with my oxygen, my chlorine with my oxygen to follow my XO and AO formula here, or kind of equation template, bring everybody's charges along. Potassium's a +1, oxygen's a -2, chlorine's a +3, oxygen's a -2. And if I make each of these compounds neutral, then it's going to be K2O and Cl2O3. Our option then is letter A. So your correct answer on that one was letter A. All right. Number 23, asking which of the following will decompose to form a diatomic element. So they're all going to go through decomposition. Which will make a diatomic element? Well, when water decomposes, you're going to get hydrogen and oxygen. That's one of those binary compounds. It's just going to break apart into its 2 elements nearly always. And that's what's happening here. Both of those are diatomic. So it's obviously that one, right? But what do the other ones have for choices? NaClO. That's going to break down as a ternary salt. And NaClO, then we get sodium with oxygen and chlorine with oxygen. I'll just give you those formulas. You could go through and figure out the correct formulas based on their oxidation numbers and all that, but neither of those is a diatomic element. H2SO3, that's an acid. It's going to break down to give us water and a nonmetal oxide, in this case SO2. Again, neither one of those is a diatomic element. And then finally, Na3P will break down to give us sodium and phosphorus. Two elements, but neither one diatomic. So our choice on 23 is A. Question 24, we're putting together a non-metal oxide, P2O5, with water. And according to our template examples we've been looking at, this is one of those cases where we're going to make an acid. This is a non-metal oxide, AO, plus water to produce an acid, which our formula generally is HAO. Right? Put those together, though, we need to know that HAO, which in this case is hydrogen, phosphorus, oxygen, isn't everything, right? We need to bring the charges along from the other side and make that formula come out correctly. So oxygen as usual, -2. Hydrogen as usual, +1. And for phosphorus, then our oxidation number is based on the fact that there are 2 phosphorus for every 5 oxygen. If the 5 oxygen are each -2, that means a -10 total on the oxygen side. Phosphorus to get to +10, the phosphorus each must be +5. 2 times 5 is 10, 5 times 2 is 10, that compound's neutral. Why does that matter? Well, because those charges are going to come along as always to this side, and we put them together on this side as such. All right. Now the temptation here is to make an easy mistake, and that is to say, oh, I've got +1 and +5. That's a total of +6. And +6 means I need 3 oxygens to balance it out. And I'll put 3 on the oxygen, call it a day. Now, I'm going to clear this out so we've got a little more space to work here. But that's not going to get the job done. Okay? Reason being, when our hydrogen and our phosphorus and our oxygen come together to give us an overall, in the end, compound that we can name HPO3, which sort of makes a little sense at first, in terms of this is now neutral, right? +6 and -6. We can't name that properly because PO3, an ion from my gold ion sheet, my polyatomic ion list, is a real thing, but it has a -3 charge. And so in order for PO3 to be part of my acid, I would have to have 3 hydrogens to go with it, being that PO3 has a -3 charge. So even as we look at option D here, which is not correct, PO3 in my ion list has a -3 charge overall, and hydrogen has a +1 charge. So I'd at least have to have a 3 here for that to be correct. That doesn't work. But it is going to combine to make an acid, and so at least if I can look at my list and know that the only other acid that's here is letter A, okay, I know that that's the correct answer. But how do we determine that that's the correct answer? Becomes the challenge. Okay? I'm not going to have HPO3, but instead I'm going to use those same elements, okay, to put together the H3PO4 and show you how that comes about. Like, why does it turn out to be H3PO4? I'm going to switch to a little thicker pen here. Apologize. This is kind of being a little bit of a turd here, and I don't want to go quite that thin. Okay, so how does this come together if not HPO3, as we've determined isn't correct? Well, what you need to remember is that whatever we come up with is something we can name, and H3PO4 we could name as phosphoric acid. But if I didn't give you the multiple choice options, and you know in the test you won't have multiple choice, how do we figure this out? Well, if in this case getting 6 positives from the H and the P, hydrogen and phosphorus, and 6 negatives from the oxygen doesn't work, and we're going to have to try something bigger. We're going to try something larger. Obviously, 2 oxygens here doesn't work because 2 times -2 is -4, and that comes up short of the 6 positive that I have on my H's and P's alone. So we can try trial and error, but I don't like trial and error as a general rule because students don't see the reasoning behind trial and error, and I don't blame them. There really isn't much there. So how do we figure it out here? Well, if I look at my ion list and I know that I have a choice of PO4 as a possible polyatomic ion, what matters is that in my ion, the phosphorus needs a +5 charge and the oxygen needs a -2 charge. These have to be held up. And if I look at PO4 and think about this as a +5 and a -2, just because I looked it up on my ion list and I saw phosphorus and oxygen together, well, does that add up to -3? And the answer is yes. 4 times -2 makes -8. 1 phosphorus times +5 makes +5. And when I put these together, I get -3. So sure enough, PO4 is the correct ion to go on my acid. Okay, here. Trick now being that in order to make that compound come out neutrally, I've got 4 -2s, that's -8. I need +8 over here for my hydrogens and my phosphorus. So I'm gonna need 3 hydrogens to get there. 3 hydrogens makes +3. Phosphorus is another +5. That's a total of +8. And then oxygen takes care of the -8 by itself, H3PO4. And it's something, importantly, that we can name. As far as it goes with our test, nothing on the product side of any equation that you write is something that you can't name. If you've done it correctly, it should be something that you can name based on what we've worked with throughout the year to date. If you see something there that's like, wow, I couldn't even name that, what did I make? It's probably not correct. Okay, that's a really good rule of thumb. 25, which is the most likely to result in incomplete combustion? Remember, incomplete combustion means oxygen is in shortage or is going to start to run out. Okay? Eventually, you're going to run out of oxygen or start to run short. Okay? So, shortage of O2. In which of these cases is there a shortage of O2? Well, in the Bunsen burner in the lab, obviously there's lots of oxygen around because we're all feeling perfectly fine and not lightheaded, hopefully. Burning a log in a bonfire, say in the summertime, well, heck, it's nice outside, there's lots of air around, there's going to be lots of oxygen around. And even lighting a birthday candle and a cake, that's not even burning very much, but even there, you're in an open room with people, there's plenty of oxygen around. Using a gas grill in your garage is a very bad idea because it's likely to eventually turn into incomplete combustion, if not burn down your whole house. Why? Well, in your garage, there's a limited amount of oxygen as if the doors are closed, and even with the doors somewhat cracked, you can create a pretty short oxygen environment. Carbon monoxide will start to build up, could suffocate you, could kill you, could infiltrate your house, could get to your family and guests. So using a gas grill in your garage is not a great idea. If it's too cold to roll your grill outside in the wintertime and use it outside, then use your stove inside instead. Don't light a gas grill in your garage, for crying out loud. Dumb idea. All right, 26. This is a single replacement reaction, right? Aluminum is going to come in and bump HNO3 out. So aluminum is going to bump hydrogen out of HNO3. Why hydrogen? Well, if I look at my activity series of metals, aluminum is a metal, obviously. Hydrogen isn't a metal, but it acts like one. So what's going to happen is aluminum tries to kick hydrogen out. Can it? Yes, if I look at my activity series of metals, okay, hydrogen is quite low on the list, aluminum is fairly high on the list. So aluminum can kick hydrogen out and take its place. And when aluminum does that, it's going to join the nitrate ion that hydrogen is currently with and make a new compound, which we see here in our options as aluminum nitrate. And the hydrogen comes out as a gas, so choice B is our answer. Don't forget in that case that hydrogen is a diatomic element, so it's coming out in twos. As the hydrogen is being replaced, they join into pairs and make hydrogen gas, aluminum nitrate. Okay, there you go. If aluminum was ranked below hydrogen on the activity series, then you would choose no reaction because aluminum couldn't kick hydrogen out of its compound. But as it is, aluminum can. 27, another single replacement reaction here. Fluorine is a non-metal. It's really important that you recognize that right away. People get really excited about trying to kick out whatever's first in the compound. Aluminum's first, you're getting kicked out. Well, no, aluminum is a metal, right? And chlorine is another non-metal. Don't forget, we need to identify this first because the elements will replace those whom they resemble. So non-metal fluorine will try to replace not aluminum, but the non-metal chlorine that it resembles. And can it? Yes, again, check your activity series for non-metals, and you'll see fluorine is at the top. Fluorine can replace all other non-metals because it's so aggressively reactive. So fluorine will kick chlorine out of aluminum chloride here, and chlorine will be off on its own, which we see here, and nowhere else. And aluminum will be with fluorine now as the new partnership, which we see here, and nowhere else. So choice A is our correct answer. B is a common misconception of students where they think that the fluorine kicks the aluminum out. They just kick out whatever's first. That doesn't work. That's not how it's going to shake out. And D would look more like a synthesis reaction, which we wouldn't deal with for this. Okay. Final question, 28. Which of the metals below is considered least active? That means go to my activity series and find the one that's lowest on the list. Okay. The very, very bottom are the precious metals, including gold. Gold is near the bottom of every activity series, no matter what source you use, along with platinum, silver, copper. Some of those rare metals that we know are very valuable. Those tend to be the least active because they're stable and they last for many, many years. So a gold bar is least active, but highly sought by people who want valuable metals to save for investments and so forth. So gold, very, very low on the activity series, very high value, and it's one of the least active metals around, and certainly on this list, the lowest of the bunch. So that's 28 questions from our review. Hopefully you realize some of your weaknesses, or maybe you found you don't have any. That would be even better. If you have questions that you still want answered, try to run up some time with a teacher yet, whether your test is coming up on the next day you're in class or a couple days later. Try your best to find some time or email your teachers even with a question, and we'll see if we can help you out. Talk to you then.